Okay. So in stars, we've got nuclear fusion, basically. Okay. So stars are these huge balls of hydrogen gas, but they're only mostly hydrogen gas. There aren't only. Okay. So at the center of the star, you've got hydrogen nuclei, and they are undergoing nuclear fusion. Okay. In this nuclear fusion, they form helium. Okay. Now remember when we were talking about fusion, how it changes, literally it changes form from something else. Okay. So we've got one type of hydrogen called deuterium and another type of hydrogen called tritium. Okay. And they're both isotopes of hydrogen. Okay. Now, obviously, there are other fusion reactions in the star. Okay. Now, the reason fusion in the star is so common is because at that heat, it is very difficult for things to not constantly format because heat creates change. Heat provides the energy. Okay. So, in this reaction of deuterium and tritium reacting, it releases a lot of energy. Okay.
Yeah.
And so this energy is really what powers the reaction. But this energy is what creates the heat to make further reactions happen. Right?
Yeah.
Okay. So there's a show, Our Universe. You should totally watch it. Okay. It's voiced by God. Joking. It's voiced by Morgan.
At this point, he is most role.
It's voiced by Morgan Freeman, and it's really, really good. When I can't sleep, I watch it. Okay.
All right.
So, the universe is a large collection of billions of galaxies. Okay, and they say the universe. I would claim that it would be a universe, not the universe, but I mean, let's go with their theory here. Okay. A galaxy is a large collection of billions of stars and out. Okay. So stars are large astronomical objects like the sun. Now, the Milky Way is one of billions of galaxies. Okay. So it's a huge collection of stars. Now, the sun is only one of the stars that make up the Milky Way. Okay. And other stars in the Milky Way are much further away from Earth than the sun is. So some of these suns also have around them. Okay. Now, when we look at distance, space, we count it in years, but not just years, light years. Okay. How the distance traveled by light in 1 year. Okay. So the Milky Way is approximately 100,000 light years away. So if light had to start on the one side of the Milky Way, it would take 100,000 years for it to get to the other side. Okay. Now, a light year is approximately 9.5. We're going to do meters because we generally do calculations in meters. 9.5 times to the power of 50. That's how far it is.
Yeah.
Okay. So now, how are stars formed? Okay. They go through like a lifestyle. They start off as a nebula, then a protostar, now protostar beginning, and then they become a stable star. Okay, so basically what happens is a cloud of gas and dust, nebula, starts to get a gravitational attraction size, right? And so what happens is all of these particles get pulled closer together. And when they get pulled closer together, what do we have when we've got different gases together? They're going to go through reaction. And so then they generate heat. So then this hot ball of gas becomes a protostar. Okay. But then because of this heat and all these reactions, it generates mass. And the increased mass pulls more things. Okay. But this increase in mass and pulling things to it also creates higher density. Okay? Because things are more packed. And what happens when density increases?
Increases.
Pardon?
The gravity, no.
Pressure increase. Pressure increase. Lower energy happen. Okay? So what happens is by it becoming denser, the collisions happen frequently. And so what happens is the temperature increases. Eventually, the temperature increases so much it becomes hot enough that nuclear fusion happens at core. And this is basically not just an element turns into another form of that element, it's hydrogen turns into helium. Okay? So there's constantly, it's searching for equilibrium the whole time. And by constantly searching for equilibrium, it's going to constantly shift back and forth from one thing to the other. Okay? Now, the gravitational forces are acting inward. Okay? So, constantly what's happening is the outward layers are being pulled inward. Okay? So, with the outward layers being pulled inward, that's the gravity. We've also got the thermal pressure. Thermal pressure acts outward. So it's this constant turning of everything. Okay? And so eventually it creates a stable system. And so by creating the stable system, by reaching this equilibrium, instead of being this messy nebula or a protostar that's kind of small, it's found its vibe, and the boundaries of it are more clear. Okay? So now this star can either, this is a main sequence star, so this can either then become a red giant star, a planetary nebula, which will then be pulled into the white dwarf, and then it'll become a black dwarf. Okay? Or it could become a red supergiant star, which turns into a supernova, which can then either turn into a black hole or a neutron star. Okay.
Okay.
Now, a red giant basically happens where after billions of years, the hydrogen starts to run out. So what happens is with the hydrogen running out, we basically we're struggling with that equilibrium. Okay. So when this happens, the rate of fusion increases. Okay. So what happens is the core shrinks and it causes the core to heat up. Because of
Pressure.
because previously we had things pushing out, the heat pushing out, but now we've got pressure increasing the core. Okay,
Yeah.
so the energy produced by the fusion decreases, so gravity becomes greater than the outward force due to thermal pressure. Okay, so eventually what happens is the star becomes a red giant, and the core becomes hot enough for helium to turn into carbon. Okay, so we had hydrogen turn into helium turns into carbon.
Carbon.
Okay, now what happens is when this helium turns into carbon, the energy released is reignited. Basically, the fusion reactions that get reignited, the outer layers, start the expansion and cooling. Okay, and then we've got a planetary nebula. Okay, so when the helium in the core then runs out, so we've had the hydrogen run out, then we've got the helium. When this helium runs out and it's all turned to carbon, then fusion doesn't continue. So the star becomes unstable and the core collapses for its own gravity. Okay? And so everything that's left then is thrown out as a planetary nebula. But now we've just said that it makes carbon. Now, what is something that all things on Earth have in common, all living things?
Made of carbon.
Made of carbon. Okay?
Yeah.
Now, the collapsed core that exists then, okay, in the middle of this nebula, planetary nebula, is called a white dwarf. Okay? So, over time, the amount of energy it produces starts to decrease. Okay. Now, that's for a smaller star. Okay. When we've got a bigger star, it becomes a red supergiant. Okay. Now, the red giant happens after billions of years. The red supergiant happens after millions of years. Okay. So it burns hot but short. So the hydrogen begins to run out much faster. Okay. Now, similar to the low mass star, the rate of fusion decreases and the core shrinks and heats up. So it becomes this red supergiant. Okay. Again, helium starts to form in carbon. Okay. So again, we've got the core starts to collapse and it creates a supernova. So once iron has been formed, okay, so we've got this loop of fusion. So once iron is formed, the fusion reactions can't keep going. Okay, so what will happen is the core will just very, very rapidly start to collapse. And it will create, by collapsing, it will create a giant explosion called supernova, which we've heard before. Okay, now at the center of this, we've got a very dense body called the neutron. Okay, so again, the outer layers of the star made of iron and carbon are going to be ejected into space, forming new clouds of dust and gas, nebulas, which will eventually stars. Okay. Now, this nebula might also then create new stars with orbiting planets. So it might hit orbiting planets and create whole new stars. Okay. Now, a neutron star is what? It's what do you think it is?
A collection of all the ingredients needed to create a star, but it hasn't an unformed star.
No, a
No.
neutron star happens after a supernova when it's the core of the supernova. Now, there is so much gravity in this core of the supernova that it keeps pulling in, okay? And it is very, very bright. But then suddenly it pulls in so much that it's so dense that not even light can escape from the pressure.
Like a black hole.
That black hole.
Yeah.
Interesting.
Yeah, I do. Huh.
I hear the buzz around. We fly with skies and trees. We break the chains that bind. Take lessons from the bees, from earth to moving parts. They teach us how to stop, bringing the